Isn't.
So this exercise today is we want to use our vectors to help us prove things like a geometry proof, but using vectors. So a lot of our geometry properties are going to come into play here. Our first one says to prove that the line joining the apex of an isosceles triangle to the midpoint of the base is perpendicular to the base. So the first thing you will have to set up is you'll have to set up a diagram. You have to set up all your own labels, okay, which is very annoying for me as a marker because everyone will do it differently and I've got to follow everyone's things individually. Okay, so what I'm going to do, I'm going to draw a triangle over here, an isosceles triangle. And I'm going to call it A, B, and O. So I'm going to turn them into position vectors. So I'm going to prove actually, let's start again. I'm not going to prove yet. I'm going to say let triangle OAB be isosceles with OA equal to OB. Okay, so these sides here, they're my ones that are going to be equal. All right, I also have a point M. So M is going to be the midpoint of AB. Okay, so put that in there. There's my midpoint M, and I'm going to connect that up with O. Just to make things convenient, I'm then going to be able to say let little vector A be equal to OA, and I'm going to also call little vector B OB. So that then gives us some direction to work with. So OA going that direction is going to be little vector A. OB going that direction is going to be little vector B. Okay, that also tells us, because it's isosceles, we know that the length of vector A is going to be equal to the length of vector B. Okay, now we're trying to prove that the base, the AB, is perpendicular to the OM. So if I can find expressions for both of them and times them together to make 0, that should help me prove it, right? Okay, so let's find an expression for OM. OM. If I start at the O to get to the M, I would need to start with vector OA, and I would want to add on the base of that triangle is AB, and I want half of it. So I'm not going to write AM because I don't know an expression for AM, but I could get one for AB. So I'm going to call that half of vector AB, which would be what the OM is equal to, right? Now, OA is what? In red, written in red. It is the little vector A, plus half. The AB, if I'm going from the A to the B, it would be B minus A, correct. So that's going to be bracket vector B minus vector A. Is everybody else okay with that, or is that just Ben? Yeah, we're good with that? So starting with capital A here, I would have to reverse the vector A to get going in the right direction, which is why it's a negative A. The B is in the right direction, so it's a positive B. Ashton? You're looking confused. No, we're good? Okay. You got it?
I think I got it.
Okay, then I'm going to expand that out because I'm going to be able to collect up some things here. So I've got little vector A plus half vector B minus half vector A, and that means that the 1 vector A minus half vector A would be half vector A plus half vector B, which could factorize the half back out of it again.
Is that a minus sign or a times between A and B?
Whereabouts?
Third line from the bottom.
Third line, there's a plus for the first one, and this one here's a minus.
Okay.
Okay, so that's OM. Now, as I said, I'm going to multiply, oh, I'm running out of room here, so we're going to have to write small. I'm going to have to multiply the OM with the AB. That's a multiply. Now, OM I just found. OM is going to be equal to the half bracket vector A plus vector B. I haven't worked this out yet, but we can. What would be an expression for AB? Well, we can't, sorry? B minus A again.
Is that a times?
It is a times.
Okay.
Yes, it is.
Dot.
B or a dot, yes, minus A. Now, if we're going to multiply vectors, remember that it's not a full FOIL thing. You're just multiplying the first ones with the first ones because like the ABs will cancel out. For that reason, might actually be easier to rewrite that so that let's put the B first in both brackets. You don't have to, but it just makes it easier to see them multiply. Because when you multiply those vectors, let's leave the half out the front, all we do is multiply the vector B times vector B, which is going to be the length of vector B squared. Remember, that's how you do that when you multiply two vectors together. And then you're going to multiply vector A with negative vector A, so negative vector A squared. But remember, way up here, that the length of A is equal to the length of B. So instead of having vector B squared, length of B squared minus length of A squared, I'm really just subtracting the same thing from itself. And that in that bracket would just be equal to 0. Okay, so I would say, maybe you could put out the side here, since the length of A is equal to the length of B, that means that whole thing is going to be equal to 0. Okay, and because when I've multiplied those two lines I got 0, that means that they are perpendicular. So you could write a little, therefore OM is perpendicular to AB. All right, this first one done. The problem with these questions, I think, is knowing where to start a lot of the time. What is it that we can do to actually prove the property? Let's try another one. Everyone finished writing that? Not quite.
Yeah.
Yeah, you got it. All right, question 2. An interval AB with a center O. All right, so we have an interval, a line, that means, going from A to B. There it is. It has with a center O, so that's like my midpoint, center O in there. Subtends a right angle at a point P. So somewhere out here, that's going to subtend out there a right angle at a point P. Prove that a circle with a diameter of AB, so if we were to draw a circle going through the A and the B, O would obviously be the center, going through the A and the B, that the circle would also pass through P. That is actually a property of what we call circle geometry, that the angle in a semicircle is always a right angle. Okay, so not something that we've seen before, but it is actually a geometry proof, a fact. So we've got to prove it though with our vectors. So if AB is going to be a diameter of my circle, I'm going to start by putting a few more labels in here. I'm going to say that R, because it's going to be a radius, right, from O to A. So from O to A, I'm going to put this in red, O to A, that is going to be my vector R. little vector p for going from O to P, because I'm going to have to join that up as well. So let's join a line down there from O to P, and that is going to be my little vector P. That does mean I can draw a little conclusion there. Therefore, OB, what do you think OB has to be? O is the center. Negative R. So let's put a negative R there, because the OB is going in the opposite direction to OA, so it would be a negative R. All right, so we are trying to prove a right angle again. So we need to try and, we know that it's a right angle, and we're trying to show that the length of the R is going to be equal to the length of the vector P, because that would mean that that point P would be on the radius of that circle. Yes, but we have the right angle to help us prove that. Okay, so let's find an expression for the BP and the AP, the two sides that are connecting up that right angle. So let's start with the OB. Oh, I forgot to write that down here. OB was going to be equal to negative R. I was in the middle of writing that and started talking about something else. So let's start with BP. Can I write an expression in terms of little r and little p for BP? Starting at the B, I would need to reverse the negative r, so it'd be a positive r, and then plus the p. Okay, so that's going to be equal to vector r plus vector p. All right, then we're going to also find an expression for AP, doing a similar thing. If I start at the A, I'm going to have to reverse the R again, going the other direction. So it's going to be negative R and plus P, or let's put the P first, P minus R. I know that those two vectors are making a right angle. So I know that BP times by AP is going to be equal to 0. I don't have to prove that this time. I'm told that there's a right angle there, so I'm using that. So if I sub in for BP that I have vector R plus vector P that I just found, and for AP that's P minus R is equal to 0.
That's a times, right?
Times in between the two brackets,
Yeah.
yes, dot or a times.
Yeah.
Like I did last time, because I'm going to multiply these out, let's put our letters in the same order. So I'll shift that first bracket around to be P plus R equals 0. And then I will times them out. What happens when I times them out? I do vector P times vector P, which is the length of P squared. And then I have a minus length of R squared is equal to 0. Now I could move the R across the length of R squared across the other side, like that. And if I square root both sides, I then get that the length of P is equal to the length of R, which is exactly what I was trying to prove. Okay, I've now shown that the length from O to P is the same as the radius, which means that P is also sitting on that circle. Okay, so just write a little conclusion down the bottom. So I'm just going to say, therefore, OP is equal to OA, which is equal to OB. So all of those things are equal. And A, B, and P are all points on the circle, whoops, so A, so on the circle with diameter AB. Yes? Okay, good. One more. And then your turn to practice. There's not a lot of questions in your exercise, but they may prove a little bit time consuming. Okay, question 3. You did all that written down? Yes? Okay, cool. Question 3, prove that the base angles of an isosceles triangle are equal. And my head says to me right now, can I just use a congruence proof? Because that would be so much easier. But we're practicing vectors, so let's deal with vectors instead. Okay, so we're going to make up our own triangle again. So it's pretty much going to be the same triangle as I used in the first question. So I'm going to do a triangle over here, an isosceles triangle. I'm going to have the A and the B down the bottom here, O up the top. So I'll start my little, because we're making up all of this information, it's customary to kind of write down what you're putting in there. So we start by saying, let triangle OAB be isosceles with the OA equal to the OB. So you're stating which things are the same. There they are. OA equals OB. Then we're going to let vector AB be equal to our little a again, and OB be equal to our little b. So,
You mean OA?
oh yeah, sorry, thank you. I wrote the wrong thing, you're right. OA. I want to go from O. So from O to A, that way is going to be little vector A. O to B, going that way, is little vector B. Just like last time. So that leaves me with the one I was trying to find next, which was AB. What would be an expression for vector AB?
A minus B?
B minus A.
B minus A. Or the same thing, really. No, it isn't. Never mind.
Oh, I called them different on my thing, that's why. It would be B minus A.
So it actually.
I just made a dumb mistake.
Okay, so we are now going to find angle A. We need to show that the base angles of our isosceles triangle are the same. So to find angle A. Now, I probably should put one more vector line on there. This one down here is going to be A, no, not A. Oh, can I change
B
it?
minus A.
I think I want to change it because I'll have too many minus signs in there. Let's rewrite it. I'm going to change the direction, sorry, because I want that to be a plus. If I change this to be AO instead, sorry.
Oh my goodness.
I just don't want to have too many minus signs when I do my dot product in a minute.
1 second, miss.
Why?
Knowing what's coming. That will mean, sorry, that means it's going to change that one too. If I change that direction, it means that I can add those instead. So vector A plus vector B, which makes this a nicer thing down here. Because we're setting the question up, we can choose which way we want those vectors to go. Okay, so finding angle A, as I gave a clue away, we're going to be using dot product here because we learned that we could find an angle by doing the two vectors that are making the angle multiplied together is equal to the length of each vector multiplied together times cos of the angle in between. Do you remember that formula? Should I write it down for you? It went something like this. It was A times B, not those A's and B's, this is just the general formula, not for this specific case, was the length of A times the length of B times cos of theta, being the angle in between them. Okay, so that was a formula we learnt about in our last lesson. So I'm going to apply this to my isosceles triangle. All right, I'm going to start with my, as I said, capital A down here. I'm not going to rearrange that formula. I'm going to put it straight into that formula as I've written it there, which means my vectors that I'm multiplying are going to be vector A that I'm multiplying with A plus B. So this is why I didn't want the minus signs in there. Okay, that's going to be equal to the length of A times the length of A plus B times cos of the angle in between them, which was A. The other thing that I probably should have mentioned, just check that your vectors were going the right way. Remember when you're using that formula that the vectors need to be tail to tail, which they are for that first one, tail to tail, which was also good that I turned that vector around so that they were tail to tail. And I have my first formula. I can expand the left-hand side out. So vector A times vector A is going to be vector, the length of A squared plus A times B. And none of this, I can't simplify anything on the right-hand side, so I'm writing all that down again. Okay, so that is going to be what I'm going to call equation 1. Maybe you can see where this is going. I'm now going to do a second one where I find angle B using the same formula. However, this time I have to be extra careful because my vectors on angle B over here are tip to tip, not the correct way. I need them tail to tail, which means I need to reverse both of those vectors. So vector B that I actually need, I need that to be a negative vector B because I need it going the other direction, so that's tail. And the A plus B, I also need to put a minus sign in front of that so that that is going the opposite direction.
Is that times?
Yes, it's a times, it's a dot. Dot means times.
Comma. I thought the dot's supposed to be
This is why I often just write time signs.
I thought the dot has to be like halfway up.
Yeah.
Or maybe a comma.
A comma.
Yeah, I thought it was a comma.
All right, let's keep going. They are going to equal, we're using this formula up here in the corner again, the length of B. Now, if I want the length of B, does that minus sign matter? No, because it's a length. So it's the length of B, and I'm going to multiply that with the length of A plus B and cos of the angle in between, which is my capital B angle. Now, like last time, let's expand out our left-hand side.
Is that the cosine rule?
It comes from the cosine rule, yes. The two minus signs are just going to become a plus, which is convenient. I'm going to have an A times a vector B, and then I'm going to have a plus, because the two minus signs cancelled out, the length of vector B squared, times by all of that stuff on the right again.
So when you times B by itself, it just straight up becomes length.
Yes, it does. That was one of the rules we learnt about, I think, in 8B. I think it was 8B we did that.
Yeah, well, I'm not very...
Okay, not finished with that equation yet. I'm trying to do some simultaneous equations here. That's the goal. I'm trying to get a relationship between angle A and angle B. I'm hoping that they're equal. That's what I'm trying to prove. I'm trying to prove it's isosceles.
Well, you can set the A plus B in there.
You're on the right track, but something easier first. Something easier first. It's isosceles. So remember that the length of A is equal to the length of B.
Oh, you can just replace that.
So I can just go through that second equation, and everywhere where I have the length of B, I'm going to change it into length of A. So A times little b is going to be plus vector A squared equals length of A plus, not plus, sorry, times, times length of A plus B cos of B. And that is going to be my equation 2. Now have a close look at the two equations, equation 1 and equation 2.
Because it's the same.
See how you got length of A squared plus AB, length of A squared plus AB. So I can sub one equation into the other and those two parts will just disappear. So if I write this down, it's going to be sub 1 into 2. And that means that it would just be length of A times A length of A plus B, cos A, is going to be equal to length of A times length of A plus B, cos B. Does that make sense how I got that? Or you just writing it down and not really knowing what I'm doing here? Does it make sense or not?
Oh, it'll make sense after I've written it
Oh,
down.
no, I get it.
You get it? Good. Now have a really close look at those. I have a length of A, everything's multiplied, and I have a length of A here and length of A here. I could divide those away, and I have A plus B, length of that there, and length of that there. All that stuff can just cancel off. So all that is left is that cos of A is equal to cos of B, and then we can just get rid of the causes, which means that A is equal to B. Angle A is equal to angle B, which means that the base angles of that isosceles triangle are equal. We've proved it. So hence, the base angles of triangle OAB are equal. And that is it.